We want to create a mesh using 2D finite element method. Firstly, we can see Young's modulus and Poisson's ratio are defined here. Then we can see node per element and Gauss point per element, which should be 3 for triangle elements and 4 for quad elements according to our preference. The problem dimension is 2 since we are working on 2D. D1 and D2 state the dimensions of our complete mesh. P and M are the parameters that define our mesh density. If we choose to include a hole in our mesh, its radius can be set here. Let's try our code and see what happens. Here you can see our mesh with a hole with 0.2 meters radius. Let us run our code with r equals 0.1 meters. The difference between them can be seen in the figures. The element type is defined here. You can choose to create mesh with triangle or quad elements depending on the preference. Here you can see a mesh created with quad elements. In order to change the element type to triangle, we should change the node per element and Gauss point per element from 4 to 3. You can see a mesh created with triangle elements as expected. Our code has also a feature to create uniform or hollow meshes. Both function takes the parameters shown and gives node list and element list as output. If a uniform mesh is desired to be created, one must change the code to uniform mesh. Here you can see a uniform mesh created with uniform mesh function. If we want to create a mesh with a hole, we can use void mesh function. Let's create an hollow mesh with a quad elements and proceed with the description of the code. In void mesh function, we can arrange the location of the hole using R1 and R2 parameters. Here, you can see a hole located at the origin. Let us change R1 by 0.1 and run the code again. We can observe that the hole is slided towards right by 0.1 meters. Same procedure applies in both axes and can be monitored in the figures. Here, boundary condition type is selected. If 1 is selected, the brick is extended from both sides. If 2 is selected, the brick expands from all 4 sides. If 1 or 2 is selected, the one must implement a displacement. If 3 is preferred, one must exert a force and the brick is under compression, which is a suitable boundary condition for our project. Here, you can see how boundary conditions are applied into the code. -1 indicates Dirichlet and otherwise there is Neumann boundary condition. We can solve our system with the parameters shown here, just like in project 1. Enough talking with the code. Let us proceed with our problem. We want to investigate whether a hole and its location in a brick affects its durability and strength. If yes, how critically the structure is affected. The presence of a hole gives engineers advantages, such as low production costs and more space for cement that stick bricks together. Due to these benefits, hollow bricks are used since 1850s. Therefore, our aim is to find out how critical are the drawbacks that engineers have to deal with when they construct a house with hollow bricks. Let's build a brick that has a uniform and dense mesh to begin our analysis. Let's set the parameters P and M to 40 to have a dense mesh. Arrange element type to quad. Node per element and Gauss point per element 4. BC type to 3. In order to have a compression analysis, we estimated the force value according to data we obtained during our research. We use void mesh function to create a hollow brick. R1 and R2 are 0 to have a hole located in the origin. In this section, the maximum stress in YY direction can be observed with different hole locations as seen in the figures. We use uniform mesh function to create uniform brick. All other parameters that define mesh are held constant. To sum up, we detected that the hole must be located as close to the origin as possible, and the hollow bricks are almost as durable as uniform bricks. Therefore, considering the advantages of hollow bricks mentioned earlier, we can say that the hollow bricks are better choice for construction. Thanks for watching.